I'm going to be talking about what comes after HTTP 1.1 and what it takes to move past there, and well, why we even want to move past HTTP 1.1. And so I guess briefly, I just want to introduce myself a little bit more. So yeah, I've worked on traffic infrastructure at Facebook for 2.5 years. Mainly my day job is working on the reverse proxy, so that's the front end. Whenever you make an HTTP request to Facebook, it's going through our reverse proxy that we're load balancing across all of our web servers. And as such, we're the layer of software that's first interpreting the HTTP request, since we need to look at various parameters to figure out which web server it needs to go to. And so because of that, we've implemented HTTP parsers, and that also gives us the opportunity to implement any successive protocol that comes after HTTP, or is at the same layer. Okay, so I broke up the talk basically into a few different parts. I want to start with the motivation, what the opportunity is moving past HTTP 1.1. Then I want to give a quick crash course on some of the solutions that we've come up with. Mainly, this is going to be mainly covering SPDY, but good news is like SPDY is HTTP 2. They did a copy paste a year and a half ago, and then we've worked since then to evolve it and fix it from that point. Give a little bit of experience of what it's been like running SPDY at Facebook, and then what's new in HTTP 2. Yeah, okay. So why do we want to rock the boat and mess with the HTTP layer? It's already pretty complex. Do we really want to get in there and muck around? And the answer is well, ideally no, but there's so much performance we're leaving on the floor that it would be crazy not to go in there. So let's consider a user that's in Seoul connecting to a Facebook data center in Oregon. So the round trip is pretty big. It's about 95 milliseconds. And so they're like, great, we want to talk to Facebook. We want to go fetch the newsfeed. Well, first, you need to establish your TCP connection. And right there, you've burned 100 milliseconds doing pretty much nothing. Great, we've got a TCP connection. Oh, wait, we really want security too, right? I don't want the NSA snooping on my request. So a few more round trips, okay? So finally, 300 milliseconds elapsed, and now we can actually make our HTTP request, which is what we wanted to do in the first place. So all this is to say that setting up new connections is expensive. It's expensive because your user is not looking at your website. It's looking at a spinning bar. You're not even getting progressive page loads. You're sitting there waiting for your connection to get ready. And there's a few optimizations you can do in these layers before HTTP. You can have TLS tickets, so you can give you can change the SSL handshake to 1 round trip instead of 2. But you're still doing 2 round trips, so that's 200 milliseconds. There's some really audacious proposals to get rid of the TCP round trip, but that's not widely supported yet. That's called TCP snap start. It's something Google's been working on. It'd be cool if it works out, but there will always be people that don't implement it. And so it's much easier to change user space code or change things at higher levels, such as HTTP, if you want to do these optimizations. So, OK, we want to use fewer connections, right? OK, well, actually, I'll talk a little bit more about why HTTP is so connection heavy later. But first, to pound it even more, why we don't want to open a connection. So let's assume, OK, so we've got the full TCP handshake finished, SSL handshake finished. Now we actually want to transfer some data. OK, still have to wait. We have to go through slow start, OK? So when we start out with slow start, we're pretty slow. Then we have to exponentially ramp up our congestion window. This might look like a familiar graph from back in your early networking classes. And then finally, at some point, your congestion window goes above the actual capacity of the network. And then you get packet loss or a timeout. And then you enter a phase called congestion avoidance. And congestion avoidance is really the state that you want to be in. It's the steady state of TCP where you're closely modeling what the actual network capacity is. Any state before that, well, you can see during exponential, all that area to the above and to the left of that exponential curve is wasted opportunity, where you could have been serving bytes on that connection, but because you just open a new connection, you don't know what the capacity of this network is, so you have to go through slow start. So we want to stay in congestion avoidance. So again, like reuse your connections, don't open new connections if you can avoid it. Okay, so let's take a quick detour for a little bit of review, just in case anyone's a little bit rusty on HTTP 1.1. This is basically what HTTP 1.1 looks like on the wire, assuming you're not encrypting it or anything. Like this is the plain text HTTP 1.1 request. So you have get, which is your method. You have some path. You have your version identifier, and then you have a bunch of headers. Looks pretty simple. All right. And then we have our response. Again, our version, status code 200. OK, great, we got it. And then a bunch of headers. OK, so we're good. We're smart this time because we know that we want to reuse connections because we heard that making new connections is bad. So for our second request, we're going to reuse this connection. And we'll fetch something else. And lo and behold, it's to the same host, same caching properties, same user agent, same language. And then we have a response. And it also looks very similar. And I don't know about you, but this looks like a lot of redundant information. So there's a lot of opportunity here to cut out the redundancy, save bytes on the wire, lower people's data bills. And indeed, if we model, OK, so here's, it doesn't show up very well, but there's a line around 300 bytes. On the x-axis are responses from a large website. I forget exactly which website. But basically, this is the amount of metadata that it comes with every single request, or for every single response, excuse me. Mark Nottingham is the guy who collected this data. He's the chair of the HTTP Biz working group, which is the standards body developing HTTP 2.0. And so he noticed that like the average response header size was around 300, 350. And then if you just throw gzip onto those headers, you get an immediate 6x reduction in bytes on the wire for the metadata, that is. So there's obviously a lot of room to grow there. So OK, so we've got the intuition. Like there's a lot of redundancy, and we want to reduce our connections, our number of connections. OK. But OK, one of the things I've heard is that people really don't like that HTTP2 and SPDY are binary protocols. But actually, it's much simpler. So I can't draw that nice picture that I did with HTTP 1.1 request and response, but I can write code that's like 10 times shorter, 10 times simpler, and much less likely to have bugs. And personally, if it comes down to this, like I'd rather just have fewer bugs than a nice example that I can show on a PowerPoint slide. And the reason it's simpler is because every single byte of that HTTP1 request in the metadata could be a control character. So I have to parse every single character, see if it's a new line. If it's a new line, OK, now I'm in the header section. OK, go ahead. Oh, now the header name is over. Now I have to keep scanning. OK, now the carriage return. Whereas with HTTP2 and SPDY, everything is length encoded. So you know what the format of the header looks like. So for each string, it's like, OK, this string is 10 bytes long. Great. Jump here, mem copy, or just reference into it. You can jump over that. You don't have to scan every single character. So we've benchmarked SPDY versus HTTP on plain text connections. So like just really testing the parsing engine of HTTP 1.1 versus SPDY. And we get 60% higher requests per second using our SPDY parser. So a lot of opportunity there for reducing your server weight or your client weight. This might take the form of a little bit less battery usage on your phone if it's talking SPDY. Again, a good indication that there's room for improvement over HTTP 1.1. And it's also TLS everywhere anyway. So if you hook up Wireshark and you just monitor your HTTP requests, chances are you're going to see SSL opaque bytes. You're not going to be able to just look at the wire and see that. It's kind of gone are the days of just being able to like telnet to a host and like type in get foo and like hit enter and have the response come back. It's kind of cool to do when you're first like trying out your HTTP server or like connecting to the internet for the first time, but like that's not how the internet works nowadays. Everything's encrypted. So you need tools anyway to actually even look at the real plain text bytes inside of a SSL connection. And yeah, so tools can help you here, and you can even build a renderer for your speedy connection so that it looks exactly like HTTP. So it's just it's a tools problem that's easily solvable, and the wins are so big going to binary that I think it's a very clear decision. Okay, so quick refresher here, just so everyone knows what we're talking about. Okay, so when people talk about HTTPS, that really is two protocols combined. It's HTTP layered on top of TLS, essentially, or SSL. And below that, that's always running on top of TCP IP. When people are talking about SPDY or HTTP2, really it's HTTP2 is layered on top of TLS. It's sort of wedged in there in the session layer. And then HTTP as a protocol still sits on the top. So the semantics of HTTP 1.1 are unchanged in HTTP 2. HTTP 2 is actually really a framing layer for HTTP 1.1. So it's not really replacing HTTP 1.1. It's more like making a more efficient representation that should just sort of work transparently behind your normal HTTP APIs. So the good news is, as a developer, when people implement HTTP 2, you're just going to get faster performance, and your APIs don't even have to change at all. And all the semantics that you know about with get requests, head requests, put requests, post requests, that all stays the same. Okay, so let's get back to the problem with HTTP 1.1 and connections. So you might have been thinking to yourself, okay, I'm not supposed to open new connections. That's great. There's a bunch of ways in HTTP 1 that I can reuse the same connection. I don't have to open new connections. One of those ways is pipelining. You might have heard of this. It's sort of a way that you can issue multiple requests to a web server and then have that web server process those and then return them in order. So basically, it looks like this. You can make a bunch of requests all at once. You don't have to wait for the response before you make the next request. Web server can kick off jobs, compute the results, and then stream them back to you. But there's an issue here. These endpoints are not equal. That expensive endpoint took a long time to render. And meanwhile, we had some really small resource that is instantaneous to return. And then there was some other resource that really should come first, but we requested it in the wrong order. But because of HTTP 1.1 pipelining semantics, the response has to come in the same order. This problem is called head-of-line blocking. And it's a problem that SPDY had to solve multiple times, as well as HTTP 2. Every time we'd fix one of the problems with head-of-line blocking, we'd find another one. And we'll get into that. So the real answer here is multiplexing. So what is multiplexing? It means out of order. It means parallel. And it means that you can always make useful progress on that stream no matter what kind of request pattern the client is making. So let me give you a brief demo of what multiplexing looks like in practice. So this is for SPDY 2, which is sort of the earliest version of multiplexing that really worked. Basically, we have this frame called a SYN stream. It basically wraps up your GET request and metadata that's associated with HTTP request. FIN means we're done with the request side. There's a stream ID associated with each. So this allows you to map from, a stream ID is basically maps to an individual request or response. And then we get a reply with some metadata. But FIN is false. That means there's more data coming. Okay, then there's some data. And then we make a request on a new request, so stream ID 3. Requests are always odd-numbered streams. Okay, great. And then we make another request for 5. And then it just so happens that 5 was really fast to respond, so we can send the response metadata associated with that in the SYN reply. The body data was also readily available, so then that request is done, or that response is done. And then finally, number 3 finished up, and then we can send that response and close everything down. So unlike in the first example with HTTP 1.1 pipelining, every single response was able to proceed when it was able to. So pipelining works okay if like all your resources are the same. Like imagine fetching a bunch of static resources or images. It works pretty well for that, but it does not work for general purpose dynamic traffic that could have longer or shorter response times. Okay, cool. So we've got multiplexing, right? Well, not quite. So there's a problem with denial of service. Not in the sense that you're going to take down the server, but you're just going to have bad performance. So imagine you have a big post that you're making, and you're streaming tons of data, like a video upload. Then let's say the server is memory pressured. So it doesn't want to accept, like, say it has to buffer the entire video before it can, like, render it or something. But like, for some reason, it's not able to store everything in data in memory for a certain period of time. So what's it going to do? It has to stop reading the data somehow off the TCP stream. If you keep reading off the TCP stream, like, it's going to eventually run out of memory or something. Okay, well, SPDY2 doesn't leave us many options. We have to stop reading from the TCP socket. Well, that sucks because now the second GET request, while we're streaming a bunch of data, it turns out, oh, I just want that really small thing. And it tries to make that request, but it's not listening on the TCP socket anymore. So that essentially we get back into the same problem with HTTP 1.1 pipelining, where the first post has to completely finish before that GET request is seen. It might not have to completely finish, but there's going to be a delay. And there would be no memory commitment from the server for that GET request. So there's no reason it couldn't serve it. It just wasn't listening. So how do we fix that? Well, the answer you may not like, but we're doing flow control, just like in TCP, but now in the HTTP layer. So now there's two rounds of flow control going on, one in the TCP layer, one in the HTTP layer. So let's say we're streaming some data to the server, and now the server is basically saying, OK, sorry, maybe that doesn't show up right, but it's saying, like, I've acknowledged 100 bytes. You've sent me 100 bytes, and I've processed it. You can now send another 100 bytes. Basically, the way it works is that you have like a 64K window, and you can always send 64K without waiting for any window updates. And then when finally, if that counter reaches 0, then you can't send any more bytes. And then the server or the remote side is responsible for sending a window update to allow you to send more. And it's bidirectional. So the same thing with the response. If the client can't read all of the response, it can stop sending window updates. And then eventually the server's send window will go to 0 and it won't send anymore. But in this case, the client was able to process it and send a window update for those 50 bytes because it processed it, rendered it. OK, so cool. We've got multiplexing now, right? Well, not quite. There's another DOS problem. OK, so servers really want to make this minimal resource commitment. If we have let's see here. If we have two posts going on at once, basically, they could both be streaming a lot of data. And so you might say you can control this with the SPDY3 flow control windows. But if you open up the maximum number of concurrent streams all streaming there, it still might be too much data. So what's the solution here? We could make the window smaller per stream. That has performance impact because then you're going to be sending more window updates on the wire. Because if your windows are really small, then you're going to have to frequently tell the other guy, like, OK, yeah, you can send. Yeah, you can send. But if you have a large window, you can delay that and wait and sort of do bulk updates for your windows. And we also want to have a large number of concurrent streams, maximum, because we want to be able to process things in multiplex. But if you do the product of your maximum parallel streams times the window size, that might be more data than you're willing to commit to a single connection. So, and this problem particularly shows up in proxies, which I had some personal experience with. So the only other solution is to introduce a third flow control window. So yeah. Basically, what you can do is if you get, you maintain another window that's per connection. And so for every single bit of data you get, you have to acknowledge both on the per stream, or per request window, and then also on the per connection window. It's basically, you can send as long as neither the connection nor the stream window is blocked. So if the connection level window is blocked, you can't send body data. But what it does allow is other requests to come in. So if we get that small little request, we're still listening on the TCP socket, unlike before. Because now even if we're under memory pressure, we can continue to read bytes off the memory, off the socket, because we know that the client's not going to make us commit to buffering more body. So if the parentheses is the stream ID. So we get a window update for one. Oh, sorry, the animation's a little messed up. OK, so we get data on stream 1, and then we send a window update for stream 1 and also for stream 0. Stream 0 is the connection. And then similarly in the other direction, when the client receives data, it sends a window update on both. Now, it's not always sending window updates for every single piece of body data it gets. That would be just really screw our data efficiency. Instead, you batch it. The algorithm that most people use is when your window goes below half, then you send a bulk update for that. You can do more tricky things like calculate the bandwidth delay product and try and time it just right, but it's not really worth it. You might as well just do something simple. Yeah, go for it.
What are the practical implications of doing flow control bytes like on speed?
Yeah, so what are the practical impacts? What, sorry? Yeah, what's the problem with are there any problems associated with doing flow control at 3 layers? In practice, no. It's just a little bit inefficient. You could imagine a scheme where you just do it once right, or maybe just twice. It's still in progress, figuring out if there's, I'll get to it in the end, but there's some other experimental protocols that are trying to eliminate the TCP layer, which would allow multiplexing without that extra flow control. OK, so quick experience with SPDY that we've had at Facebook. So basically, I work on this project called Proxygen. It's a collection of HTTP libraries, and we've built proxies out of it. We've built HTTP servers out of it, also clients. We're even shipping it on our mobile phones nowadays. And so Proxygen was first launched sort of end of 2011. This was our reverse proxy. That was our first application. And then we kind of early on realized that it wasn't quite correct for working with multiplexed protocols because we were connection oriented, but to do multiplexing correctly, you need to be request oriented. So we did a refactor. And then we advocated for SPDY for the HTTP2 spec. And we got our wish. HTTP2 was based off of SPDY2. We did our first SPDY2 tests end of 2012, launched it, and then we also rolled out SPDY3 and 3.1. Our architecture is basically, there's a 4-part architecture. Basically, we have a session layer, a codec, transaction handler. I don't think I need to get into all the details here. But the data flows from the socket through a session layer. Our codec is responsible for serializing and deserializing the bytes on the wire into higher level data structures. We have a transaction for each request response pair. And then there's a handler that basically listens for OK, I got some headers. OK, I got some body data. And so pretty exciting. We're going to be open sourcing this framework pretty soon. The proxy logic in the middle, we're not open sourcing just because it's too hard. It's really baked into our infrastructure. But this abstraction will be open sourced pretty soon, hopefully within a couple weeks. So look out for that. OK, and so was it worth it? At the end of the day, how much does SPDY really buy you? And the answer is yes, it's definitely worth it. So compared to HTTPS requests, we saw an 88% reduction in the number of handshakes that we were doing. So this is all that wasted work I was talking about in the very beginning with the TCP and SSL handshakes. So that was reduced by 88% by using SPDY. Because you can use a far smaller number of connections to serve all those requests. Even compared to HTTP without SSL, SPDY over TLS was a 69% reduction in handshakes. Just because of and for HTTP, that's only one round trip for TCP, yeah?
But what exactly was the test? Because I can imagine that if you compare just with one request, it's not going to be the same as if you pipeline 100 requests via SPDY. So kind of what were the parameters of this?
Of these numbers? Yeah, so it's averaged, right? So like if you have a keep alive connection, like the first request on there will have we have a metric called connection cost, which is the number of round trips before any useful work was done. So like if it's a new TCP connection with a ticket, that's a connection cost of 2. If it's a full SSL handshake and TCP handshake, it's 3. And so for the first request, it's going to be some number, and then in SPDY, all the consequent ones are 0. And so if you take the average over all requests on a particular connection, the connection cost goes down by this amount. So basically, we're serving more requests and responses per connection with SPDY than we are with HTTPS. Does that make sense?
Yeah.
Okay. And so basically, this translated into, across the entire website, a 200 millisecond win per request on average. So we're done, right? Okay, not quite. So the story doesn't end with SPDY. This talk is mainly about HTTP2, or maybe you thought it was about HTTP2, but it was actually about SPDY. It's basically the same thing. But there's a number of issues that have come up. And the biggest one is security related. We can't gzip headers. So CRIME is the name of an attack. It stands for Compression Ratio Info Leak Made Easy. It's a really good backronym. It came out in 2012. It affects every protocol that's using compression inside of TLS. So it works by the attacker controlling the plain text, and in this case, particularly by injecting headers, and then observing the size of the ciphertext. And so if the attacker can inject a header value that matches, like say, part of your cookie, then it compresses well. If it misses, then your ciphertext will be larger. So by doing sort of a scan this way, in linear time, you can actually recover the cookie and do a session hijack. So it requires the attacker to control the client. So maybe it's not as bad as like a passive attack where you're just like listening on the wire. But still basically ruled out gzip for HTTP2. So enter HPACK. So unfortunately, fortunately, it doesn't have prefix matching. Prefix matching based compression is sort of the common problem with gzip. If you can match a small substring, you get the full benefit of that. You get some like progressive benefit of compression. Whereas with HPACK, you have to have a full token matching before any compression actually applies. So that breaks the linear attacks back to an exponential. Like you'd have to guess the entire cookie. So names and values are opaque to the algorithms. They're just strings. And the encoder gets to control whether to compress. So like, for instance, you can even say like, never compress the cookie. So, and that also prevents other things from being compressed based on that cookie value. So you can just sort of like blacklist certain headers if you just consider them too important. But it's complex. There's a static table of symbols. Basically, the way it works is if you have a match in one of these tables, you just index into that and say like, give me index 5. And that's like, oh, that's the string content length or whatever. So there's a static table that comprises all those common things like the string get, the string head, the string content length that show up all the time. And there's a dynamic table because maybe you have headers that are a different workload. There's Huffman encoding for when you actually do omit a string literal, you Huffman encode it, save a little bit of bytes there. And it used to be even more complex with like delta encoding. And like it was like a 1% gain, and like people are like, okay, this is just getting too complex. Let's cut it out. Yeah. So this theme continues. Like there's a lot of edge cases. How do you handle huge headers? We have these frames where everything's length encoded, right? So what if your length is so big that you can't fit it in the number of bytes that you've reserved for the length itself? So we have to have continuation frames. So like your header frame ends, and then you have to have continuations. This came up with Kerberos tickets, because apparently those can get huge. Proxying HTTP 1.1 to HTTP 2. Again, a lot of complexity there. How am I doing on time? Great? Okay. How much time do I have left? Any time?
As much as you want.
Okay. Okay. Yeah. Okay, so proxying HTTP 1.1 to HTTP 2. there were a number of issues there as well. So, OK, so let's talk about priorities. Another feature that came with SPDY and is also in HTTP2 is like the notion of a priority. So say you issue 2 requests, you can say, I want this one with some preference over this one. And basically, it's a hint to the server or the proxy or whatever is handling your request to like prioritize bytes for that stream. But there's a few issues associated with it. So let's say like you have 2 clients. So assume all of the connections here are SPDY. You have one mobile phone connected to the load balancer, and the load balancer is connected to the server. The load balancer is doing a full SPDY demux and remux. So it's an HTTP load balancer. It gets the request, OK, and then it forwards it on. OK, simple. Now we've got a stream of bytes coming back. Priority is increased. So like P1 is higher than P0. So a second request comes. OK, goes to the load balancer, establishes a second stream. And so now the issue is this other phone, which has no relationship to the other one. You'd imagine they should get equal priority on the backbone link. But because the priority is forwarded like this, on this backbone link, the bytes for this one client will be preferred over the other client. So that's a little bit sucky that one client can DOS the other client. And it's really like a load balancer having like one connection, like multiplexing multiple connections from clients to one server is like one of the primary like arguments for having a load balancer in the first case. So opening more connections between the load balancer and server is sort of a non-starter. OK, so how does HTTP2 fix this? Well, it added complexity. This is the theme. OK, so a few things here. There's now weights and groups. So you can have priority groups. And within that priority group, you can have a relative weight compared to your peers in that group. It's actually represented through a tree structure. We don't need to get into all the details there. But basically, the load balancer can receive this. And because it's hop by hop, HTTP2 is hop by hop, it can rewrite this. Now it's in group 1. So group 0 is like the entire connection. Group 1 is associated with one particular request. Actually, that part's not important. Yeah, it's just a separate priority group. It can rewrite that and then forward it to the server. And so there's one stream. And then similarly, another GET request. This guy has like, it's weight 16. It's not as important. Fine. Puts it in a different priority group. It keeps the weight of 16, though. And this actually establishes a fair flow on the backbone load balancer to server because they're in separate priority groups. And separate priority groups get equal weighting. So only if you're in the same grouping do the weights come into play. So if you make a consequent request on that, if the clients make more requests, those requests will get bound into the same priority groups from the edge to the origin. Sorry, edge is the load balancer, origin is the server. And so basically, the internal tree representation looks a little bit like this. OK, another feature. This is a cool one. I think I have high hopes for this. I don't know how much control or how much visibility HTML will get into this. I think it would be cool, but I haven't heard positive things from Chrome. But basically, server push is a way that you can push resources opportunistically to the client before they even request it. So let's say they request the home page. You can return with that home page, but then you can also push more resources. And the way it's implemented today, it goes straight into the browser cache. So your JavaScript won't ever know that things were pushed. It's just that you make the request for the resource, and it's already there. So the reason you might push is because you know that like inside of that page, you've referenced some static resources, for instance. Now, it's really tricky to do this, right? Like the server has to know a priori that you don't have it cached. Otherwise, you're wasting bytes in the network. So that's a very hard problem. And no one's really gotten a slam dunk on it yet, like knowing how to predict what the cache is. There's some proposals for like extra metadata to like update the cache information. Nothing like totally simple or figured out yet. My hope for server push is like I would like to see JavaScript hooks for when these server push resources arrive. It would be cool to have like asynchronous actions that fire when something's pushed to you. You could imagine layering You can imagine layering other protocols on top of server push. So right now there is a proposal for WebSockets for HTTP 2. And there are some other protocols for HTTP 1.1 that were layered on top. But HTTP 2 is still sort of in flux, so people are like a little hesitant to build protocols on top of it already. That hasn't stopped us. Actually, we're experimenting with it. But it turns out because Facebook controls both the client, like we have an app, and the server, we can do experiments easily since we control the entire network there. But yeah, so the hope is to get support for other protocols like WebSockets. But for HTTP 2, the focus is mainly on just supporting tunneling HTTP 1.1 on top of it. It's more of a goal for HTTP 3 to like have more general multiplexing support. But I think it pretty much can work for many other protocols. We're working on MQTT tunneled over SPDY and also HTTP 2. I don't know if have you guys heard of MQTT? It's a pub sub kind of protocol that allows you to like, we use it for chat. So you can like subscribe to a channel and like get data streamed to you when like there's like a group thread or something like that. And so yeah, TCP may not even be the future of HTTP. We might go back to the drawing board and go to UDP. That would be the ideal. Unfortunately, like there's a big problem with NATs and other network resources that basically only let TCP through, which is kind of like, well, that kind of stops that. There's been some experiments, like UDP reachability for Google at least is like 91% from their phones. But it sort of depends. Like we have yet to run experiments on that ourselves. But there's sort of strong consensus that, yeah, like there's a lot of repeated work going on with the duplicated flow control. Anyway, so here's some resources. They have a nice GitHub page. It's actually really nice. They have an FAQ, should answer a lot of questions. And there's also a mailing list where you can follow the flame wars and everything. So yeah, I'd be happy to take some questions.
So when is it supposed to be standardized, like projected?
Yeah. So we've exited working group last call. So it's now going to the IESG last call. And after that point, if they have any issues, there's like a small number of open issues that we have to fix. And then as long as that issue list remains empty, we'll go to RFC. And so that should happen early next year. Like I would expect RFC like Q1 2015. Yeah.
Are there parts of HTTP 2 that are not part of SPDY, or is SPDY just really?
The question is like, anything new in HTTP 2? So the new things in HTTP 2 are the priority groups, HPACK. There's a number of other, like a lot of bug fixes. And there's a few other things I didn't get into. Like, it's pulled out of the main spec, but there's something called alternative services that allows you to like, it's more applicable if you're a CDN, like Akamai really wanted this feature. Basically, it allows you to point a user like, okay, you connected and you want this resource, I'll give it to you, but like, really you should go to this other place that's like geographically closer to you or better for some reason. And allows you to like sort of gracefully shed over to another server. Yeah.
How much of the spec do other clients support? Web browsers?
How many, like, of the HTTP2 spec?
Yeah.
Well, like the ones, so we cut branches. Well, actually, it's more like snapshots. We don't like have forked revisions or anything. But like draft 14 is the latest. And Chrome, Firefox, and a bunch of Internet Explorer also, Opera. All the major browsers actually are implementing HTTP2, and a bunch of servers. Unfortunately, Facebook does not yet have it. We're hurrying. We're going to try and get into interop testing before we get to RFC. We don't anticipate any big blockers. Like we've been contributing based on our experience with SPDY 3.1, with a few bugs that we found there that we fixed in HTTP2. Anything?
How have you seen the Western world or American adoption of HTTP2, or in general, like projected implementation of it compared to like third world countries, Africa, India, Brazil?
So there's always going to be clients that like, you know, like these feature phones that like are never going to upgrade. It's too bad, but like I don't know. There's not much you can do about that. Like, I think it really comes down to like how new is your software stack, and like what's your update story. All the major browsers that I listed will have it, and all of these have like auto update functionality. So I think the uptick will be very fast. Like wherever you use Chrome, Firefox, Opera, or Internet Explorer. Well, Internet Explorer doesn't have quite as good of an upgrade story, but I think like the adoption will be pretty high, pretty quick.
So in the future, when I'm trying to like debug some problem in my circuit,
I was going to mention that.
yeah. So like, what about that?
Curl supports HTTP2.
Oh, it does.
Yeah,
Oh.
or it does. I don't know if it's been pushed out to like all the major packages, but it does. Yeah,
I guess it's still the question of like, given that
it's like extra complexity for the server.
that's just something that we need to worry about.
Yeah,
On both the server and like testing it.
sure. Yeah, I mean, the HTTP 1.1 is probably never going to die. That's just like the fact of the matter. The good thing is HTTP 2 gives a very good, I didn't talk about how it's negotiated. Right now, you can do it over plain text with HTTP upgrade. You can also do it in the SSL handshake. There's an extension to TLS that allows you to pick your next protocol. And you can just agree on, like, we're going to talk HTTP2, and just like, bam, you're talking HTTP2. Since now we have that TLS extension, it should be really easy to go to HTTP3 or HTTP4 after that. There's like a list of protocols you advertise. It's a very simple like agreement on like what's going to happen there. So the upgrade story for 2 to 3 and consequent is very good. But yeah, there's always going to be HTTP 1.1. Yeah.
So when the server makes like these agreements with the client, like about how large their windows are, what happens if the client isn't that active and it tries to push more data than the server lets it? Does it just drop packets? Or?
Right. Yeah, good question. So if the client or SPDY is pretty symmetric, and HTTP2 as well, you just basically talk about yourself and the remote side. For most of the flow control stuff, it's completely symmetric. If the remote side violates your flow control window, you send a reset stream, which basically cancels that request or response. And then if they continue to act badly, then you basically need to build in heuristics that like there's an official mechanism for this in HTTP2 called enhance your calm. You say like enhance your calm, like chill out, like you're like doing bad stuff. And then if they continue to like do bad things, you can just hang up.
Okay.
Yeah.
I guess I'm curious, so when you were modeling the expected gain of implementing everything, and when you actually implemented everything, how close were you to projections?
It was a while ago. It's a good question. I think we had good reason to believe. I don't know if we did. This work, any projection work might have started before I joined the company, actually. The SPDY project began right as I joined, so the projection stuff might have been a little bit before that. Yeah, I don't know. I mean, I think there was very, very good reason to believe it, and already good data published from Google, and our workload is very similar. So, yeah, we trust our friends at Google. Yeah.
So how do I get this on my website?
Okay. So there are a number of implementations out there. I don't think Nginx has it, or are they working on it? Not that I know of.
They're working. I think it's Jeff released at some point in the next few months. Last I read.
Yeah.
I guess.
So there are a few implementers. There are a few libraries implementing it. libcurl, you can always use that. When I open source our stuff, you can use our HTTP server. Although HTTP2 support is not complete yet. I mean, that'll come in a couple months. It may not be available to the general public for another few months. The big shops are going to be the ones first adopting this. Yeah. Right. So your web server will also need to, if you want all the bells and whistles, your HTTP server will also have to speak HTTP2. Because, for instance, server push, all the hops have to be HTTP2. HTTP2 was built with compatibility with HTTP1 in mind. So you You can have like HTTP2, then HTTP1, then HTTP2, and like back and forth. That's fine, but you just won't get the end-to-end like prioritization or push won't work. Yeah.
So I those schemes to the pipe. So
Send the window updates.
Yeah. So who actually has the need for this kind of fine-grained control over how the connection goes?
It matters if you want to reduce the number of connections and you want high concurrency of requests. So like if you have a website that needs many requests or like has a lot of assets that need to be loaded, you'll if the performance of that loading is important to you, then using this is like what you need. Now as for like who's controlling the logic of when to send these window updates, this is all handled inside the HTTP library layer. As long as like the way it works in our framework is like you can at any time just say like pause, and then like the library will stop sending window updates and everything will back off. And your API is just like pause or unpause. So like all that complexity is hidden behind like, or should, if it's a good library, should be hidden behind like abstraction, So, I mean, yeah, like debugging it is hard, but like, that's why we have people who write libraries. Anything else?
So if I develop applications that use WebSockets and I want to use HTTP2, WebSockets will go like a separate stream over HTTP 1.1?
So for now, if you want to use WebSockets, probably you're going to use an HTTP 1.1 connection and then upgrade that to WebSockets. It's separate for now. However, there is a proposal for like how to do it over HTTP2. It may or may not actually work. It's not tested. Yeah. It's based off an older draft, and like it hasn't been updated for some of the latest breaking changes. Cool.